So there it is. So I broke down, this is homework number 11. I'm breaking down the 136. It's 2 times 68, 2 times 34, 2 times 17. So we have a 2, a 2, a 2, and a 17 are the ends of the trees, the leaves. 2 cubed times 17. Those are the primes, the building blocks of the 136. So they're what make the 136. So now, how do we find all the factors? What do? We do the same thing we did a minute ago. We do the box thing, right? We good with that? So do you realize that terminology when they say find all factors or find all divisors, that means do the box thing. Those are all the numbers that go into a number. So start with a 1, and I'm going to go down here, times 2, times 2, times 2, that's 2 cubed, right? And up here, 17, and that's as far as we go there. And then just multiply those together. How are we doing? Will you recognize that on the exam next Wednesday? They say list all factors. So this is not new, is it? This is kind of like a little review. Just want to make sure you would recognize it kind of out of context. That's why I give you a practice exam. Because, everything's all mixed up. And that's a little harder than homework, right? Just because it's all mixed up and it's all together at once. And so practice that practice exam. Even over the weekend would be a good plan. You don't have any other plans this weekend, right? Nothing but math was on your calendar, right? So that practice exam is there for you. You can do it again and again. I know that probably seems crazy. But I would do it again and again until I get 90% at least on that thing. All right, let's do it. 1, 17, 2, 34, 4, and 4 times 17 is 68, 8, and then this is the 136. Those are all the numbers, and we're done. That's it. That's all the numbers that divide evenly into 136. Making sense? We good? Questions, just like we did before? All right. Okay. So, whoops, where am I at? I did the wrong one there. There we go. So number 2. Find the smallest counting number that has the following number of divisors. 1. So, yeah.
I'm sorry. For number 1 on B, for 60, we end up with 3 primes. Like 3.
Oh, different primes. Is that true? I think you're right, because it's 5 times. Yeah, you're right, because 60 is 6 times 10, 2, 3, 2, 5. Right, so you have 2 squared, 3, 5. Yeah, so, okay. So, yeah, good question. Let's see that real quick. So, 1B, 60 is 2 times 30, 5 times 6, 2 times, however you want to break it down. Ends up being 2 squared times 3 times 5. I'll just get rid of all this. Whoops. Okay, yeah, so what do we do when there's 3? Going to have to add another little slash. I'll show you. So you just say, okay. Yeah, because I haven't really shown this. I said it would never happen. I thought it would never happen. Here it is once. So 2 squared, I'll start with 1, and go times 2 times 2. So I'm doing this guy first. And then I'll do this guy next. It doesn't really matter what order. So this guy's a 3. Let me give a little more space to him. 3, I'll make it a little bigger like that. So just forget about the 5 for the moment. Just pretend he's not even there. If I just had the 1 and the 3, this would be it, huh? Y'all with me so far? So it's a good question. Thanks for noticing that. So 1B has a 60. So when you break it down, it's got 3 primes. And so basically what we're trying to do is find every possible combination of those primes. That's what this method is just a way of saying, hey, what are all the ways those primes can get together? Because any way that 2 2s, a 3, and a 5 happen to get together, like maybe 1 2 with a 5, or maybe 2 2s with a 3, or maybe a 3 with a 5, or maybe just a 5 alone, and on you go. Every possible way that some of those primes get together makes a number that goes into 60, because it'll be made out of stuff that's already in 60. So you getting the big idea? That's the idea of this table and why this table works. Because we're basically saying, look, there's the building blocks of a 60, 2 2s, a 3, and a 5. So any way that some of them get together, like the 3 and the 5 get together, 15, that's got to go into 60, which you know it does. Because it's made out of stuff already in the 60. Does that make sense? So when they ask me to find all the numbers that go into 60, I say, well, that's just a matter of finding all the different ways the primes of 60, the 2 2s, a 3, and a 5, can get together. Because all the different ways that they can get together, they'll make something that goes into 60. Right? So it'd be like if they said, what are all the different groups out of people in this class? And all the different ways people can get together, all the different groups, that'd be groups that are from this class. That's what we're doing with the 60. Okay, so how do we do that then? Thinking about it like that, I'll just do the 2 and the 3. So 1, 2, 4, 1, 3. Now, what I'm going to have to do is add a slash in each box because I'm going to have a second option for the 5. That's what you have to do if there's a third prime in there. Or you could go three-dimensional, and I don't want to try to draw something three-dimensional. Basically, we need another dimension. So this is how I'm doing the third dimension, basically. So just use the upper corners of the box for now. Here we go. Let's multiply like we always do. Again, just forget about the 5. Pretend the 5's not even there for now. 1 times 1, 1 times 3. I'm not going down here. I'm just using the upper corners. 2 times 1, 2 times 3, 4 times 1, 4 times 3. Good so far? So that's just normal, except for the slashes, right? That's just normal. I haven't done anything with the 5, have I? Those are all the different groups of 2s and 3s that can get together. Those are all the different things that can be made out of 2s or 3s, right? None of them use a 5. 5's not in any of them. So now, if we want to put 5 in the mix and say, okay, that's good. Those are all the groupings that don't have 5. Now, I've got to throw in all the groupings that do have a 5. So how do I do that? You just take all the answers you have and multiply by 5. So take that 1 times 5. Take that 3 times 5. Take that 2 times 5. Take that 6 times 5. Take that 4 times 5. Take that 12 times 5. There they are. Do you see why that gives you every possibility? Because basically the black numbers were all the combos without a 5, and the blue numbers are all the combos with a 5. So we've got everything. We got all the numbers without a 5, we got all the numbers with a 5. So we've included every possible combination of numbers there. Good question. Makes sense? So, like I said, it doesn't matter what order you do this in, but I would always save one of the numbers. If they give you 3 primes, for 3 primes, make the last prime be first power only. In other words, I would not have gone 3, 5, and I'll put the 2 squared last. Yeah, don't put the one that has a higher power last. Put one of the ones that has first power. So you could have done it this way. You could have done 2 squared times 5 and put the 3 last. That would have worked just fine. Could have got all the same answers that way. It's just going to be easier to put one of the primes that has only first power last. Because that'll give you only one other option. Either have the 5 or you don't have the 5. Is that making sense on that? This is actually a good time to stop and think. Well, actually, let's go back to this one right here. How many divisors factors, whatever, same thing. How many divisors factors did we end up? How many in this box here? How many numbers? 8 numbers, right? It's just a 4 by 2 array, right? 8 numbers, 8 factors. 8 factors. Why? Why are there 8 factors? Well, because it's a 4 by 2 array. Right. Why is it a 4 by 2 array? Well, because you had a third power and a first power, and you added a 1 in the front of each one, so that actually ended up with 4 things down and 2 things across instead of 3 and 1. Hold on, did you follow that? Really important that you get that. I'm not just playing around here. I'm about to lead you into how we're going to do all the A through whatever that was, G or H, on number 2. Here's the linchpin logic. If somebody gives you, think with me, what if I say, hey, I've got a number here, it's 2 to the third times 5 to the second. I don't even know what that number is, whatever. And I'm going to make a big array out of it. How big's the array going to be? Well, you start with 1, and then you go times 2, 2 to the first, times 2, 2 to the second, 4. But I'm just writing them as powers now. Times 2, That's as far as you go. Am I confusing you by writing with powers? That's the same thing we always do. I'm just wanting to see the powers now. Right? You could have written 2, 4, 8, same thing. Right? And then what would you do in the other direction? Times 5, times 5. So that would end up being a what? 3 by 4. 3 by 4 array. Yeah, it's 3 by 4 array. Why is it a 3 by 4 array? Look, what do you do with this power and what do you do with that power? Whoops, there I reversed them. It's a 4 by 3 array, whatever. See what ends up happening with the powers? You add 1 to both of them and multiply. Do y'all see that? That's the linchpin I want you to see. Whatever powers are on the primes, that tells you how big the array is going to be, but you also have to have the 1 and the 1. Why do we have that 1? Because that's no 2's. I don't know if you remember that rule from algebra. You know, if you have no 2's at all, 2 to the 0 power is 1. Remember, anything to the 0 power is 1? And this is no 5's. So really you have no 2's, 1 2, 2 2's or 3 2's. No 5's, 1 5 or 2 5's. Yeah, the option of choosing none, right? If I said, hey, I've got a basket, it's got 3 2's and it's got 2 5's, right? That's what this is. Pick some stuff out of the basket to take home as your parting prize today. So what would be your options? You could take 1 2, 2 2's, 3 2's, or no 2's, right? So there's actually 4 options when it comes to the 2's, aren't there? And you can grab 1 5, 2 5's, no 5's. There's actually 3 options when it comes to the 5's. Getting the hang of this? Right? So there's always one more option than there are objects. Right? If I said, yeah, in fact, I could almost do it. Yeah. Are you sure that this is nobody's drink containers? These things are just piling up. I don't know where. At the other teachers' classes. So anyway, what if I said, hey, you have options. Take whatever drink containers home you want with you today. How many actual options? You could take 1 drink container. You could take 2 drink containers. You could take all 3 drink containers. Or you could take no drink containers. How many options? 4. 1 more than the number of objects. Because you can take none. Right? So that's what we're seeing here logically. Because we're going to really use this. So I want this to be solid as a rock in your mind. Does everybody see that? Whatever the power is, you have that plus 1 options. Whatever the power, that plus 1. So it actually ends up being a 3 by 4 array, 12 different things in the box. I don't even want to find them, but I just want to know how many. Now we're into how many. I don't care what they are. Just how many are there going to be? So let me see if you're getting this. What if I gave you 7 squared times 11 to the first power? Tell me how many. That's a how. How many? It's getting worse. How many different factors, divisors, whatever, things in the box, if I was to make the whole box and blah, 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 how many things would be in the box? What do? We take the power and we add 1. Take the power and we add 1. So the box would end up being 3 by 2, 6 different divisors, right? You with me? So whatever this number is, I don't care what the number is. Whatever the number is, it would have 6 different divisors, factors. I know for sure. See the power of primes? Primes make big, what is that number? What's 11 times 49? 490 and, I don't know, what is that? 539. Is it 539? Right? What the calculator says? Yeah. That quick, 539. That's just a whopping number. That isn't like something I walk around just know off the top of my head. I'm sure you don't either. But boom, we know it's got exactly 6 numbers that go into it. We know that quick from the power of primes. Right? Because the primes are the guts. Right? We know what's in it. We know what makes it 539 tick. Okay, is this making sense? Okay, so let's go back now to, they're going to ask me, find a number. I'm building up to what we need to do for number 2. Find a number with, let's say, with 4 primes. 4 primes, I'm sorry. 4 divisors. 4 divisors, factors. 4 things that go into it. So how would you make a number that's going to end up having 4 divisors. Wouldn't you have like a prime, let's call it P, and then another prime Q, whatever? Well, in fact, I could just make some up. How about 2 to some power times 3 to some power? What powers would I need on those guys if I want to end up having an array that has, 4 boxes? What do I need? Would 1 and 2 work? Let's try it. Would first power, second power work? Let's just guess around. Guessing is a great strategy. Just start guessing, you'll start gaining insight real quick. Would that be right? If I said, hey, I got this, whatever that number is, how many divisors would that number have? It would have, remember, you add 1 and you add 1, and then you multiply those. It'd have 2 times 3, 6. Right? It would have 2 times 3. That would have 6 divisors, right? Because you would go 1, 3, 9, 1, 2, wouldn't you? Everybody seeing that? You'd have a 3 by 2 array. So remember, whatever the power is up here, right? You have to add 1 to it and add 1 to it, and then you multiply those. So that would have 6 divisors. That's not right. I want 4 divisors. I only want 4. That's too many. So let me change it. And that's not going to work. So how can I make a number that only has, let me go back to it. Let's try it again. That was too many. So what any other ideas? What powers? 1 and 1. Is that right? That would be add 1, 2 times 2. Yeah, 4 divisors. Right? That would have 4 divisors, wouldn't it? Because you'd have to put the 1 and the 1 here. You go times 2 times 3, and that'd be it. And you can figure them all out, and that'd be the divisors. Okay, now, can you tell me, so whatever that number is, what is that number? That's 6, huh? Let me put it back the way it was. 2 to the 1, 2 to the 1, that's 6. Has 4 divisors, doesn't it? Because of 1 plus 1 times 1 plus 1, right? You add 1 to each of the powers. So you see the game plan, right? You take the power, getting kind of scribbly here. You take the power plus 1 times the power plus 1. Right? That's how you know the number of divisors, right? Power plus 1 times the power plus 1. Good? So can you tell me another number that would have exactly 4 divisors? What's another one? Could I use different primes other than 2 and 3? How about 2 and 5? Those are primes, right? What powers do I want on them? First power again, right? Because that would be, power plus 1, 1 plus 1 times 1 plus 1, which is 2 times 2, 4 divisors, huh? Are you tracking with me? So that's the number 10. 10 has to have exactly 4 things that go into it. Does it? By the way, what goes into 10? 1, 2, 5, and 10. Sure enough. 4 numbers go evenly into 10, don't they? You tracking with me? All right, because it's going to make a little jump here. Now they're going to ask us. Oh, wait. Tell me another number. What's another number that has 4 divisors? What's another way to make a number? We're making numbers here. What's another way to make a number? So we got one. How about 2 other primes? We use 2 and 3, 2 and 5. What else? 3 and 5. Great. 3 and 5, both to the first power. What is that? 15. That's got to have 4 divisors also, right? Getting the pattern there? Now, is there a fundamental other way of making a number that has 4 divisors other than a prime to the first and a prime to the first? The hush falls over the crowd. Can you think of one? What else can you do to make a number? Remember the rule. The number of divisors, let me write that rule out super clear for you, is the power plus 1 times the power plus 1, right? You just multiply those together. However many, right? So for example, somebody was to give me, 2 to the third times 3 to the second times 5 to the fourth. What would I do? How many, what would be the number, the number of divisors would be what? Add 1, add 1, add 1. It would be 3 plus 1, 2 times 2 plus 1, times 4 plus 1, whatever that is. 4 times 3 times 5, that's 60? 60 divisors, wow. I don't want to find all those. That number would have 60 different things that go into it. 60 divisors. You tracking with me? You getting the hang of this? So the number of divisors is just add 1 to each of the powers and multiply those together, huh? Because that just makes a big array. Okay, so let me ask the question again. How else can you have a number with exactly 4 divisors? A number with 4 divisors. We already said you can have any prime to the first power times any other prime to the first power because, 1 plus 1 times 1 plus 1, right? Power plus 1, 2 times 2, 4 divisors, right? Any 2 primes, both to the first power, will have 2 times 2, 4 divisors, right? But what's another fundamental way I can make it? 1 prime to what power? Third. Yeah, you get it? If you just have a single prime to the third power, that's going to have 3 add 1. That's all. 4 divisors also. That's a fundamentally different way to build a number that has 4 divisors. You tracking with me? So you can take 2 different primes to the first power, and that'll be 1 plus 1 times 1 plus 1, 2 times 2, 4. Or you can take a single prime, any prime, to the third power, and it'll have 3 add 1, 4 divisors also. Okay. So what? Well, now we're ready for number 2. With all that foundational thinking, here's what number 2 asks. Here's question number 2. Find the smallest number with 4 divided. I think that's D or something, isn't it? Does it start with A as 1, A, B, C, D or something, right? Isn't that D? Find the smallest, I'm just starting off there, I'll go backwards. Find the smallest number with 4 divisors. Well, okay, now that we have all that theory behind us, we say, well, you got to basically take 1 prime to the first power times another prime to the first power because, add 1, 2 times 2, that'll have 4 divisors. Or there's another way to build numbers with 4 divisors, any prime to the third power, right? There's 2 different basic constructs for building numbers that have 4 divisors. So they're asking me for the smallest. How do I build the smallest? You can put any prime to the first and any prime to the first. So if I say, all right, make the smallest. What's the smallest prime you know? 1's not a prime, remember? 2. And what's the next smallest prime you know? 3, which is what? 6. And now, okay, yeah, but so that's the smallest thing coming out of that template, that model, that setup, right? If you're going to take any prime to the first times any other prime to the first, the smallest thing is going to be 2 to the first, 3 to the first, 6. All the other primes are bigger and will make bigger numbers. You tracking with me? 6. Now, wait a minute. What about this side? What about out of this template, this model? 2 to the third. That's the smallest prime, right? Which will be 8. So who's the winner? 6. 6 is the smallest of all numbers that has exactly 4 divisors. 8 has 4 things that go into it also. 1, 2, 4, and 8. Just like 6. 1, 2, 3, and 6. Right? They both have 4 divisors. 6 is the smallest number with 4 divisors. Tracking with me? All right, let's back up then to let's do part C. I'm going to go backwards here. Tell me what's the smallest number with 3 divisors or factors. So let me give you a second. Think about that. In other words, you got to have a prime to what power to get a number that has 3 divisors. So think about that for a second. What's it got to be? Prime to what power? 2, right? Because you always add 1, that'll have 3 divisors. Right? Number of divisors is always power plus 1. So that will have 3 divisors. And that's the only way. It's the only way to make a number with 3 divisors. So what's it going to be? What's the smallest prime I can see? If they want the smallest, I'm going to stick the smallest prime I can in there. 2 squared. 4, right? So the number 4, does 4 really have 3 divisors? 3 things that go into it? Yeah, 1, 2, and 4. See how this is working? It's telling us the truth. 4 is the smallest number with 3 divisors. Getting the hang of this? Let's try to go back to part B. Smallest number with 2 divisors. So find the smallest number with 2 divisors. So what's the model, the template for building a number with 2 divisors? Prime to what? Prime to the first, huh? Because again, the number of divisors is power plus 1. Number of divisors is power plus 1. So that number, any prime to the first power will have 2 divisors, won't it? So what's the smallest one I can make? 2 to the first. Whoop, why did I write second? 2 to the first. In other words, just 2. Does 2 have 2 divisors? Yeah, 1 and 2. It's the smallest number with 2 divisors. How about 2a? Is that okay there? What about 2a? Smallest number with 1 divisor. There's only one number, period, that has only 1 divisor. What's the only number that has only one thing that goes into it? 1. 1 only has, it's the only lonely number. I can't resist what John Lennon's line. It just fits so perfect there. All right, so let's go on to E. E asks the smallest number with 5 divisors. What's the smallest number with 5 divisors? What's the template? What's the model? P to what power? P to the 4th, because again, the number of divisors is just power plus 1. Right? So that's going to be 2 to the 4th, which is what, 16. Does 16 have 5 things? It does. 1, 2, 4, 8, and 16. 5 things go into it. Now, you might be thinking, if I was you, I'd be thinking, now wait a minute, sir, this seems really simple. You're doing all this fancy talk, but it's so simple. 5 divisors is 2 to the 4th. It's always 2 to 1 lower. But remember, we did something different with D. That's why I started with D, because that was a harder case. Well, how do you know when you do something different? If the number of divisors can be broken up another way. So let me write out what I'm saying. Well, let me just go on to F, and you'll see. F, things will change. So it's not quite as simple as it might be looking. 2F, smallest number with 6 divisors. Smallest number with 6 divisors. Now, there's more than one model, template. There's P to the 5th, of course. P to the 5th, that'll any prime to the 5th power will end up having 6 divisors. Absolutely. That's one way to make 6. Right? But there's another way to make it. There's 2 numbers that can multiply to be 6. That wasn't the case for 5. There's only one way to make 5, 1 times 5. You know what I mean? That's why 5 only had one model. 4, though, had 2 ways to do it. 2 times 2 or 1 times 4. You tracking with me? So what's the other way I can use 2 primes? How do you make 6? What powers do I need? 1 and 2, right. Because the number of divisors, right, will be 1 plus 1 times 2 plus 1, 2 times 3, 6, won't it? So there's another model for 6, like there was for 4. You tracking with me? So if there's another way to make your number, like 6 is 2 times 3 or 1 times 6. 4 is 2 times 2 or 1 times 4. So they had 2 options. 5, 3, they only have one way to do it. The only way you're going to get 5 is 1 times 5. The only way you're going to get 3 is 1 times 3. So, all right. So what? Let's try to figure this out here. Then what's the smallest thing then? 2 to the 5th. You always stick in the smallest primes you can. 2 to the 5th. What is that number? 32. Use your calculator. Okay, and now we have to compare though. What's the smallest thing we can make with the other model? We're going to stick in the smallest primes we can. Think with me here. What are the 2 smallest primes? Remember, 1's not a prime. 2 and 3. So 2 to the 1st times 3 squared. Is that the smallest way I can do that? No, why not? Yeah, it's better to stick the smaller number with the bigger power. Put the 2 squared and let the 3 go to the 1st if you're trying to make it as small as possible. Put the smaller prime in the bigger power, right? Not the way I have it. This is going to be, 18? It's better to go, it's better to put the 3 first, 3 first and put the 2 there. The order matters now. That'd be 12. 3 times 4 is 12. And by the way, both of them beat 32. Who's the overall winner? 12. 12 is the smallest number that has 6 divisors. To see how we figured that out? So we just got the 2 different models. Right? You always have the, just one lower thing, but then you have the 2 options too. And then there's 2 different ways to put in the smallest primes. All right, we're running on time. Let's try a couple more. Let's try 2h. I probably better show you that other question. 7 divisors. Smallest number with 7 divisors. So how many ways are there to make 7? Just one way. 1 times 7. So it's just going to be p to the 6. It's just going to be 2 to the 6. 64 done. So those ones are simple. Numbers like 7 or numbers where there's only one way to do them. But I says 8 divisors. Yeah, I'm going to wrap with this one and then look at that other one really quick. 8 divisors. How many ways are there to make the number 8? Let me just write them out. There's 1 times 8, of course. What else? 2 times 4 and 2 times 2 times 2. There's 3 different models here. What's going to do this? This will be any prime to the 7th. Is it confused you there's a 1 here? There's always a 1 in the other column. Right? When we make our table, even if you had like 2 to the 7th, you'd put a 1 here and then a 1 there and start with the 2's, right? So don't worry about that other 1. It's always there. So that's always there. So 2 to the 7th. What's going to be this? Prime to the 1st, prime to the 3rd. Right? Because it's got to be 1 lower than each of those to multiply and be right. And what's this one? Prime to the 1st, prime to the 1st, other prime to the 1st. To see that? Right? Because add 1, add 1, add 1, that'd be 8 different divisors. Add 1, add 1, 2 times 4, 8 different divisors. All right, so what's the smallest thing? This would be 2 to the 7th. This would be, which is what? 128, I think? Yeah. And then, now what's the smallest thing I can do with the p to the 1st, q to the 3rd? Yeah, the 2 wants to go to the 3rd and the 3 to the 1st, Which is 3 times 8, 24. That's a lot smaller. And what's the smallest thing here? 2 to the 1st, 3 to the 1st. 5 is the next smallest prime. That's 30. Who's the winner? 24 is the smallest number that has 8 divisors. With our last 2 minutes, I better divisible by 2. I'm going to just write them out. 2, 3, 4, 5, 6, 7, 8. So if you want to build, and that's what I'm going to do, if you want to build the smallest number that all those fit into, right? All those divide into it. It's divisible by all those. Some big old number like 263 or something. I don't know what it is. But something like that. Some big old number that all those go evenly into. And you want the smallest one. There's probably a bunch of them, but you want the smallest of all numbers that all those will go into. You know what you have to do? Is just break these things down. What is 4? 2 squared. 2 can't break down. It's already prime. 3 is prime. There's the breakdown of the 4. 5's already prime. 6, you know, is 2 times 3. 7's already prime. 8 is 2 to the third. So I just broke them all down to primes. So break them all down to primes. And then take one of each prime type to the highest power. That's how you will make the number. So I'm going to go through this. It's like going to the store. I'm going to go to Costco, and I'm going to buy one of everything. I'm going to buy the most expensive one. I'm going to buy the most expensive toothpaste. I'm going to buy the most expensive tires. I'm going to buy the most expensive mouthwash, whatever. Or I'm going to go one of each thing, but the most expensive brand. That's kind of what we're doing. I'm going to take 1, 2. Oh, but what's the most expensive one I see? This one. Yeah, I should have taken that one. That's the highest price, too. That's the highest power, too. I'm going to take a 3. Wait, do we see 3 squared anywhere? No, I guess not. I'm going to take a 5. That's different prime. You need every prime type. I'm going to take a 7. And that's it, right? I took one of every prime there. Multiply that together. I have no idea what that is. 20, 420. I think it's 840. Is it 840? Yeah. You just use your calculator. Does that make sense what I did there? I just broke them all down to primes, and I just went through and I grabbed one of every prime, and I took the highest one. That means they can all fit in there. They can all go, they're all in 840. And it's the smallest number. They're all in.